Hello and welcome to the MecSoft demonstration series, where you can see live demonstrations for real users and real-world applications. For more information about our products or to schedule your own live demonstration, just give us a call or visit us at www.mecsoft.com. Without further delay, we invite you to sit back and enjoy the demonstration.
So as you can tell, I have shared my desktop with you, and I have different versions of SolidWorks installed on my computer.
Yeah, I see it.
And I'm going to go ahead and load 2017 SolidWorks. Now,
Okay.
as SolidWorks starts up, you will notice that the VisualCAM plugin automatically loads inside SolidWorks. So when you go under add-ins, and you will see that the VisualCAM add-in appears right under SolidWorks. VisualCAM
Okay.
2017. So by default, the add-in is set to active and also startup, which means when you bring in a new part in SolidWorks, the VisualCAM add-in will automatically appear in SolidWorks. So there's three different entries you're going to find. One is the VisualCAM 2017 tab in your command manager, which allows you to access the CAM interface, your milling browser. You can switch to turning, and you
Very
can
good.
activate the product also. Access the help system from here. You'll also notice that the VisualCAM browser interface shows right by your feature manager design tree. So your machining browser is over on the top half of your screen, and then the machining objects browser appears on the lower half of your screen. You can switch from your feature manager design tree to the VisualCAM tab by just a single click of a button.
Okay.
And you'll find the VisualCAM menu under the Tools menu in SolidWorks. Tools and VisualCAM will give you access to the same set of controls. Selecting Learning will give you access to the Learning Resources dialog, where you can access Quick Start guides, you can access the help system for milling and turning right from here. Okay?
Okay.
All right. Now the first thing we would like to do here is go ahead and open up a part, and we'll take a look at how we can program it. All right?
Yeah.
So I'm going to go ahead and load this prismatic part in here.
Okay.
And once the part is open, we'll go ahead and show you how to work with VisualCAM to program your toolpath. Now, as you can tell here, I have the part loaded, and
Okay.
I have the CAM interface showing up right within the part. Now, the first step is you go over to the machining browser. The machining browser has two main tabs. You have Program and Simulate. And right under the Program tab, you would want to go into Machine Tool Setup. Now, in this particular tab, you're going to establish the orientation for machining, your XYZ axis orientation. So if you want to mill the part from the bottom side or underside, you need to make sure that the Z-axis is being set normal to the surface. So you can use these controls to rotate your Z-axis. So the Z is now pointing normal to the bottom face of the part. Or if your part is modeled in the intended orientation, so in this particular part, we would like to mill these pockets. So it is in the orientation of the world coordinate system. I could just say align it to the world coordinate system. So the XYZ axis orientation is aligned to the world coordinate system.
Okay.
Now, in SolidWorks, your top plane is not the XY plane, it's the X and the Z plane. So, if you model the part from the top plane, then you may have to use these controls in here to orient your coordinate system for machining. Now, once you establish the coordinate system orientation, the next step is to determine the machining process, if you're going to be doing a 2, 3-axis, 4-axis, or 5-axis machining. For 2 and 3-axis, you would set the number of axes to 3. You have 4 and 5-axis options in here as well.
Okay.
Okay. Now, once you define the machine, this information is updated and displayed under Machining Job. The next step is to select the post processor in here that you'd like to use. Now, I'm going to change the post folder location in here. I probably had it changed to a different location. So let me go ahead and find the post processor location, and we'll go ahead and update that in here in just a moment. Now, while I'm trying to load the post processor folder in here, did you have any questions? while we are working on
No,
this?
it's okay. Yeah, I follow up you.
All right. Now, what percentage of your parts require 3-axis machining, and what percentage of your parts is 2-axis?
Mostly 2-axis plus tapping and drilling is quite good for us.
Okay.
But sometimes, maybe 10% or 5% of our parts need to be finished by using the third axis. But it is simple finishing.
Okay.
I have also used 2.5 axis for SolidCAM version.
Okay.
Mhm.
So I'm going to select the post processor in here as Haas,
Has,
since that's
yeah.
the machine tool you're working with, and I would set the output file extension as .nc.
Okay.
Now in the next step, I would like to go ahead and define the workpiece. I'm going to use stock,
Yes, stock. Yeah.
box stock, and selecting copy model box will automatically establish the stock extent that you need
Okay.
for this part.
Mhm.
So you can enter in a dimension for X, Y, and Z, or you can define the stock as a part box stock in here, where you can specify an offset for X, Y, and Z.
Mhm.
Now once you have your stock defined in here, you would want to align it. So align the stock to the part. You can establish your material for it. I'm going to pick aluminum 6061, or if you're going to be cutting with a different material, you can select the material type from the list.
Okay. It's also material selection affects the aggressive or usage of the tools, or it is only giving information to us.
Selecting a material will help you determine feet and speeds based on the
Okay.
material that you
It
select.
is affecting, right? It's not only
Yes.
information.
Mhm.
Okay. Okay.
Now, as far as the tools go, you can create tools as you, select the Create Tool Edit tab. In here, you can define tools of type ball mill, flat mill, corner radius, engraving, chamfer, taper, thread mill. You got face mill, all the different types of tools. You can also establish the feet and speeds as you define the tool, and we have this load from file option in here that can provide you recommended feet and speeds based on the material you're working with.
Okay. That's good. Mm.
Now, we can also load tools from libraries. We can select load from library in here, and we can go find the tool library. I'm going to load the library inch tool library,
Mhm.
and this would load all of the tools from the library.
Okay. And also, can we create our own library as well?
Absolutely.
User. Yeah. Okay. Okay. It's
So
very
we
good.
can have tools defined under each tool type. So you can see I have 3 different types of ball mill, several types of flat mill, corner radius tool.
It is most of them already defined, but some specific tools also can be defined.
You can always do that. Absolutely.
Okay.
Now we're ready to program some toolpaths in here. So I'm going to go in to first define my origin, which is your program 0 or your work 0, which could be a work offset G54, right?
Okay. Yeah.
Choose to set it by using a pick option. You can pick a point anywhere on the part geometry,
Okay.
or you can use set stock. I can choose higher Z southwest corner, so that'll place the XYZ origin to the lower left.
Okay.
or
I understand.
In the next step, we would want to go ahead and program our toolpaths. If you select 2-axis or 2.5 axis, you have a wide range of methods, starting with roughing, facing, pocketing, profiling, V-carve, roughing, V-carving, engraving, slot machining, chamfering, hole pocketing, hole profiling, thread milling, T-slot machining. Now with the Pro configuration, you also have remachining, which is just like rest machining in 2-axis or 2.5 axis.
Okay. And also one question at that point, Uday. We have tool changer on the machine. For example, in our mill machine, we have 10 pieces, 10 slots tool changer we have. Most of them using frequently. For example, the first 6 tools I'm using frequently, and the rest of the tools I'm changing depending on design and project. And is there any option to arrange our tool changer organization into in your software? Can we also match the tool changer and the defined tool order in the
Absolutely.
software at the same time.
Yes. So the way it works is when you define your tool, you would also establish the tool number for each
Tool number, yeah, for example, yeah.
So as the first 6 tools that you're going to be using are going to be arranged 1 through 6, as you define your tools, you can assign those tool numbers for each of those tools. In this example here, I have half-an-inch tool set to
Yeah,
tool
for
number
example,
1.
right.
Quarter-inch tool is number 2.
2.
1/8 is tool number 3. The
3,
quarter
yeah.
is tool number 4.
Okay.
Then the ball mills are set to tool number 5, 6, 7, and then
6, 7. Okay.
progressively define the tools to
Mhm.
match the tool number on the machine.
Okay.
Okay? So we
Okay,
have
right.
these tools defined, and you can click on List Tools. It lists the tools that you define and has
Yeah. Okay. In order to tool numbers, it's very good.
right. So you can sort the tools in here based on tool number or
Mhm.
tool type or diameter. You can say sort them by tool numbers. It'll list them in the
Okay. Different sort options we have. Okay.
So going back to the 2-axis methods, we have different types of 2-axis operations, and as I pointed out, the remachining is available in our Pro and Premium configurations. Now, the other methods are also available in Standard and Expert configurations.
Okay.
So we would like to first pocket some of these features. So we're going to use pocketing.
Yeah.
This displays the pocket operation dialog, and you want to select the features for pocketing. So you click on Select Curve Edge Regions, and now it brings up the Property Selection Manager in SolidWorks, and you can select the features. I can right-click and choose Select Tangencies. So I can basically take advantage of all your selection tools that are available in SolidWorks.
Okay.
Select the features.
Mm-hmm.
I could also this edge in here, accept my selections. The geometries are now selected. You go to the tool, you can make a selection for the tool. I'm going to use a 1/2-inch end mill, set feet and speeds, set the clearance. You'll notice that the clearance is now set to automatic. Your cutting parameters, where you specify your tolerances for the pocket operation. If you'd like to leave any side stock or wall stock,
Okay.
you can specify the
Yeah.
stock to leave. That's a roughing operation. You specify your cut pattern. You can do offset spiral, linear spiral. We can also do high-speed cut patterns. We have like a trichordal cut pattern. You can choose high-speed cut pattern.
Mm-hmm.
Specify your step over distance. You can add a cleanup pass at the end, and you can also control the depth in here. So for the depth, there's a couple of ways to determine depth. One of the ways is you can pick the depth by selecting a top face and then the floor. That establishes the depth in here to be 1/4 of an inch. You could do that, or you don't have to enter in a depth parameter. You could select use the 3D model to detect depth, and you just have to specify your depth per cut. I could say I would like to have an 1/8-inch depth per cut. So VisualCAM can automatically determine the depth based off the 3D model.
Okay.
Specify your entry and exit parameters. You can ramp, use a linear, or you can do a helical ramp in here. You can specify the parameters, ramp entry. You can set the angle in here and the height. And you can also specify this to be applied for each level. Any additional parameters like arc fitting and sorting can all be set right in here and then generate. So in this process, you now have a pocket toolpath for up. So you can see that we have a trichordal cut pattern on the pocket toolpath. And if you'd like to change any of the parameters, you can double-click to modify the operation and make a change and then generate it. So the toolpaths are now generated. So this is now using an offset cut pattern. And you can now go to the Simulate tab, select the operation, and click Play to run the simulation. That's a cut material verification.
Okay.
Now I would like to go back in here and program a profiling operation to clean it out. So 2-axis profiling. And you can pick the boundaries in here. Select tangencies. Select those geometries. Pick a tool. I could go from a 1/2-inch to a 1/4-inch. Set the feet and speeds, clearance, cutting parameters. You could choose whether you want to climb, conventional, mixed cut. Choose inside or outside, or you could even determine the height to cut based off the 3D model. under your cut levels, again, you can do the
Use 3D
to
model.
detect depth. Specify your depth per cut. You can apply entry and exit. Arc fitting parameters, sorting, and generate. So your toolpath for profile operation is now generated. You could run a verification.
And Uday, one question in that point. Now we have here 1, 2, 3, 4 packet areas, and also we defined as tangency, toolpaths from tangency of geometry, but also use 3D detected depth you selected. For example, these pockets, one of these pockets would be different depth. It will be considered by software, or all of them has to be same depth. For example, one of them, for example, a couple of millimeter deeper than the others. In that case, we should define new job, new operation, or it's also doing at the same operation, the multiple packets with different depths.
A very good question, and you can use the determine depth using 3D model to be able to detect variable depths in here as well. And I'm going to show that to you here with an example. I'm going to go ahead and bring in another part into here, and you will see that on the other part I'm loading, there's different depths on the pockets, and you could see that these pockets are different.
Something like this, yeah. In the previous versions, we have to always select tendency one by one and define more than one operations for different depths. You know, the previous versions were not so smart like today's.
Yeah.
For that reason, it brings another additional works and additional hours to do that. It is a good feature.
So I have selected use 3D model to detect depth, and the floor of pockets are at different depths. I have specified it to go 100 thousandths per cut. And when I generate the toolpath, you will notice that the first pocket in here is going to a depth of 300 thousandths. But the second pocket in here is only going down to 1/8 of an inch. So there's a difference in the depth between the two pockets. And in just one operation, we are able to program all of these features.
Very good. Okay.
So we could do pockets, profiles in a similar fashion, hole pocketing. You could do chamfers and profiling. So I'm going to right-click and choose Simulate, and you will notice that when I do Simulate Until, it shows a simulation of all these processes.
Yeah.
You can select each operation and also slow down the pace of the simulation. Now, one of the nice things in our simulation is you can apply different colors for each operation during the simulation, so that way you identify the material that's being left from each step. So you can apply the pocket operation to have a different color, the profiling operation to use a different color for simulation. So I could right-click on the operation, go to Properties, and assign a color in here. So I can pick this for the pockets. For the profiles, I can apply a different color. I can use an aqua color. For hole pocketing, I'm going to change the color to be green. For the chamfer operation, I'm going to change the color to be red. And for the profiling, I'm going to just leave it at the default color. Now, when I go to color properties and apply the color, you'll notice that when you simulate the pocket operation, or when you go from one operation to the next, the colors are automatically set for the cut material based on what you chose.
Okay. Yeah, it's turned to blue right now.
So you notice that the chamfers are set to red in color.
Yeah. I see.
Now, starting with our expert configuration, we also to machine tool simulation in here. So we can define a 3-axis machine. So you have a Haas machine tool. I can select the machine as a Haas. You have a VF3 model built in here. And now I can go to Simulate tab and use the machine tool simulation in here. And you'll notice that it simulates with the machine tool displayed.
Yeah, our machine like that.
So this is a simulation with the machine tool.
With the machine tool.
So the machine tool simulation allows you to simulate the material removal of the stock with the machine tool visibility toggled on.
Okay, in that point, what kind of machine options, accessories can be added here? For example, like vices or other part holders can be defined, or on the beside of the part, stock part, or this is only concentrated on parts on the machine view?
This is basically just to show the material removal simulation. So if you need to display the vices, you would actually have to build it as part of the
okay, additional part on the SolidWorks maybe.
Yep. So it's primarily used just for the verification purposes in here.
Okay. Because sometimes, okay, another question. For example, I understand the principally. For example, if I, in office side, in engineering side, I'm preparing drawing, also CAD, CAM, all the things, and then I'm gonna give to my operator who is working in front of the machine. And in that point, I need to give some indicative information to him, such as which point I have already defined as reference point, how I am planning to fix the part on the machine, and what is the tool sort of the order in the tool changer, or etc., and which tools are defined on the which tool number, something like this. And according to that information, that documentation or specification, let's say, also he prepare with the raw material and place in the correct alignment, also define the correct point as a reference, and also place the tools in the tool changer accordingly. In that case, what kind of document I can generate after all the things defined in CAM software?
Sure. I'm going to definitely answer that question for you here. So we have a very nice feature called shop documentation. So
that's why
the setup in here and right click on it and then choose shop documentation. So when you select shop documentation, you can choose where you want this file to be saved, and I'm going to use template number 2, which basically gives you the description and also includes a screen capture of each and every operation that's you've been programmed. You program the toolpath here. So now, once this document is generated, it'll automatically load this in an HTML browser.
Oh, very nice.
Explorer Firefox, so you can see it shows you the part setup in here.
Okay.
It gives you the information about the material that you're working with, your stock size, the dimensions of the stock you're going to be using, total number of tools being used, the units you're working with, and also it lists the tools that you have. Tool number 1, so it basically says the first tool is number 2, you have tool number 3 and tool number 8.
Okay.
It also includes the location of your origin, as you see it right here. It shows the origin.
Yeah, I can see.
Oh, and it shows the first operation is a pocket operation, has a picture of the tool path, and also lists the tool. So this information can then be saved, and you can make it available to the operator in the shop floor.
Very good.
So this is called shop
machining time also indicates on the displays on the page. It's very good. It's very useful.
In PDF format, or you can print it out and hand it out.
Yeah. Okay. It's very good.
You can also look at the time estimates even after you compute the toolpath. Right-click and select information will tell you the machining time estimates based on the tool, the parameters. Even this information can be printed out as a summary. You can select print, just print it out.
Understand. Okay.
And then you're looking at your posted Gcode, so right-click and post. And we would like to post this to the post processor, which is going to be the Haas machine tool in here. So I'm going to right-click on it and choose Post, and select the machine tool as Haas.
Okay.
And I'll post it right on my desktop. And there's your posted Gcode. Now the code
text file already prepared. NC file. Okay.
Work offset number. It has your tool number being called, your tool height offset.
Yeah.
And then there's your code, and also output tool numbers. When you do a search for a tool, the next tool number, you can see changes to tool diameter of an 1/8 inch.
Okay.
So, now one of the powerful features in VisualCAM is the ability to save these operations, what you create or program, to a knowledge base. So when you have family of parts or similar type of parts that you'd like to program using the same sequence of operations or same workflow, all of the parameters in here are saved to a knowledge base, like your tolerance, your cut pattern, cut direction, step over, your cut levels, entry and exit. All of these parameters are saved to a template file or a knowledge base. So when you're working with similar type of parts, you would just have to go ahead and load the knowledge base without having to recreate those operations. So in this particular step, I'm going to load the knowledge base in here, and this is going to bring in all the machining operations into it. So here you can see that I have a similar part. Now, rather than having to go through the process of recreating the machining operations, I can choose load knowledge base, and I can choose the knowledge base I would like to load in here, and I'm going to pick open, and you'll notice that it automatically loads all of the machining operations from the knowledge base.
Okay.
And all I got to do is modify or edit the operation and select the features. In this particular step, I'm going to just select using flat areas, pick those faces right there, pick the cut levels, and then generate. The toolpath is automatically generated based on the 3D model.
Yeah, it's very nice.
Yeah, this is a very nice feature. The knowledge base is one step into automation. So basically, you're trying to go through the same workflow. You're just having to, edit the operation and just have to pick the geometries for machining. Okay?
Yeah, I understand. It's very nice.
Now, saving this file in SolidWorks will automatically save all of the CAM information, the machining operations that you programmed, to the same SolidWorks part. So it's not adding any additional file formats other than the files that you're writing out for the Gcode output, which is your NC file. So that's the beauty of it. So if you make a design change, you just have to go back and regenerate the toolpath, or maybe you have to reselect some of the geometries, but you don't have to start all over again.
Okay.
Now, in this particular operation we selected these loops or chain of edges using surface edges. Now, in our 2017 version, we've introduced what is called feature detection and machining. So here, if you're programming prismatic parts like these, you can identify and detect features from the part. So I can select this face, and this will automatically detect all the features on the part. So you will now notice that there is a planar face. You have these prismatic pockets in here. It identifies each of these pockets, identifies the whole features.
Yeah.
You can program these operations by just selecting these pocket features, right-click, and then select the operation. That's pocketing.
Okay.
Specify a tool in here, and then generate. So that will create a pocket operation, and the operation is created based off the features that you defined in here, and not you didn't have to go through the process of selecting any of those geometries. Now for the holes, I can right-click on the hole and choose to do a drilling or a hole pocketing or a hole profiling. It represents the cross-section of the hole. You can pick a tool and generate. You now have a hole profiling toolpath programmed for the hole. So you can always double-click to modify it. You can add additional hole features in here, select the 2 hole features, generate. So you now have 2 of the holes profiled.
Yes.
So feature detection and machining, this can be applied to a wide range of parts in here. Feature detection allows you to identify features and you can machine from those features. Now here I have an example where there are multiple features on this particular part, and I've identified each of those features and programmed them. So here you can see that on this particular part there's a planar face and we have 8 pocket features. We have the hole feature. Now all of these have been programmed by you selecting those features. And now I'm going to go to the simulation and select the operation and hit play, and that gives the simulation. So I've chosen a CNC router in here as an example for the machine tool, and you'll notice that it simulates each of these operations. You can also apply colors for each operation during simulation in here. So there's a lot of nice features that are offered in our milling module. Now, do the parts that you typically work on, are these typical something similar to these prismatic parts that you're looking at?
Yeah.
Okay.
So
there's the facing operation, and then we transition from the facing to a pocket operation.
yeah.
Any questions so far?
No, it's okay. It's nice.
Okay, great. So I'm going to go ahead and pause the simulation in here, and I can choose simulate to end. I can simulate the end of each of these operations, so that way you see the final result of the simulation. There's the profile operation that relieves the stock material. And we also have the option to remove the remnant during simulations. It automatically removes the remnant once it's simulated. Okay?
Okay.
All right. Any questions in 2.5-axis milling, feature-based machining, and milling?
It's okay. Milling is, I understand very well.
Okay. And you can also set your preferences in here, and users can customize these preferences for each of these dialogues in here. So you can choose to output arcs, or if your control can only support arcs in XY plane and not in XZ or YZ plane, all of these parameters can be established right in here.
Okay. And can you connect to my computer and, for example, one example part, can you see on the screen? I don't know the
Sure.
feature of GoTo.
Could you give me one moment, sir?
Yes. To give idea just idea for you.
Okay. Sure. We can do that. Now, before I do that, I would like to go ahead and give you a quick overview of our 3-axis machining.
Okay.
And then,
Okay. Please do that.
Once we do that, I'll go ahead and take a look at your screen, and then we can
Okay.
work on it. So I'm going to basically bring in a cavity mold in here.
Yeah. Yeah, complex surface cavity.
Yep, so you see sculpted surfaces, fillets, drafts, and all that stuff in here. So the workflow is very similar to what we did in 2-axis, but in 3-axis is a lot simpler. So we define the machining process, you define the machine tool, you define your post-processor in here. So we would like to use the Haas as the post-processor. You would select that, and then you define your workpiece, which is your stock material. You could define a stock as a box stock or part box stock, define that. And then you establish your work zero. So exactly the same steps of what we did for 2.5D.
Yeah, it's,
Now
yeah.
in 3-axis, you just go ahead and select the operation type. So you can see that with the Pro configuration, you have a wide range of 3-axis toolpath methods. You have roughing, you have re-roughing, finishing, several different types of advanced finishing, pencil tracing, remachining, curve-based machining, a lot of different 3D methods. So typically workflows start with the roughing process in here, and you'd want to pick a tool. So I'm going to use an end mill, set feet and speeds, clearance, cutting parameters, and then you hit generate. Now I didn't have to pick any surfaces or faces for machining, so VisualCAM automatically analyzes your entire part and the stock and establishes the areas for roughing. And it does roughing in levels, as you're noticing it right here. It does roughing in layers. And you could always select pause and then pick simulate to end, which runs through your simulation. So we just did a roughing operation with a large end mill, half-inch end mill. You'll notice that there are some areas where the cutter could not get in here or may not be able to effectively clean out some of those areas. So from a roughing, you can go to a re-roughing process. Now the re-roughing is a very nice feature that's offered in our Pro configurations, which is called rest machining, where you can specify, your roughing operation with a smaller tool, and it's only going to go and look at areas that weren't being able to machine with a large cutter. So when you generate a re-roughing operation, it's looking at the stock being left from the previous step. And since I changed it from 25,000 to 15,000, you'll notice that it's only cutting areas where material is being left from the previous operation.
Yeah, I understand.
So this is re-roughing, which is offered in a Pro and Premium configuration. So the Pro would be ideal for your application needs. You go from roughing down to a re-roughing operation. And then we want to do some finishing or pre-finishing, so we can start with a parallel finishing operation. Select a tool for it, so we could use a ball mill. I'm going to go with a 1/4-inch ball, specify the cutting parameters, and then set the step over distance, select generate. And this is going to create a finishing toolpath. You can display the toolpath right in here. Now you'll notice that the finishing toolpath also automatically identified the entire part. Now if you do not want it to surface on the top of the mold cavity, we can define a containment boundary where I could select this curve edge region in here. You select tangency, select that, and then generate it. So the cutter will stay inside the boundary. You can go to simulate and then select play to run the verification. So that's your finishing cut right there, pre-finishing cut. So you can always select pause and then simulate to end to run through the simulation. So there are different types of finishing operations we offer here. So this is parallel finishing. You could do finishing in levels known as D-level finishing. We also call it horizontal finishing. And I can again select the boundary in here to contain the toolpath, select the tool, specify the cutting conditions in here, and generate. So this will generate a finishing in levels operation. Okay?
Yeah.
You can also do constant 3D step over pocketing, which is a very nice toolpath method, which is also known as constant scallop machining or uniform 3D step over machining. You can specify these parameters as well. So the Pro offers you all of the advanced 3-axis machining methods. In addition to these, you can also do pencil tracing and remachining as well. Now, you can also select part surfaces for machining. Now, while this toolpath is being computed, I'm going to add another parallel finishing toolpath in here, and I'm going to use what's called part surfaces. I can select only a certain set of surfaces to be machined, and I can select those surfaces. You can see I'm highlighting those surfaces in here. I'll accept the selection, Then I can choose whether I want to keep the cutter onto the surface or go past the surface. I can set those conditions in here and generate it. So selection of surfaces for machining, and the 3D offset pocketing which you're generating just got done. You can see how nice the toolpath looks, constant, uniform 3D step over. Are you able to view that, sir?
Yeah, sure. It's very nice.
And once you have all your toolpaths programmed, you can look at the estimated machining time based on the parameters what you specified. Right-click on it and then select Post. That'll generate your output file.
Okay. Very good.
There's your posted output file.